So we have started with the work, energy and power. Yesterday we talked about work done by constant force, right? Work done is the dot product of force and displacement. So now let's discuss further topics. So let us discuss work done by a constant force. So suppose you have a graph between force and position. Okay. So suppose you have force versus position graph and you want to find out the work done from x equal to a to x equal to b. So now it's clear from this graph what is that work done. So what's the work done? It will be area under this curve, right? So suppose this force is constant, then we know that work done is equal to force multiplied by displacement. So it is force, which is length of this side, multiplied by displacement. Displacement is just length of this side, because this is position x equal to a, this is position x equal to b. So how much is the displacement? It is b minus a. So that is length of this side, right? This much distance is b, this much is a. Okay. So what is the work done from the position, what is the work done from force versus position graph? It is just area under the force versus position graph. Okay, this thing is clear. Right? And for a constant force, it is just force multiplied by displacement. Now, what would be the work done by a variable force? So this is a graph of variable force versus displacement. This is graph of variable force versus displacement. So now the force is different at different points. At this point it is this much, at this point it is this much, at this point it is this much. Okay, so its value is changing everywhere, right? So now what we'll do is, again it will be area under the curve, and we know how to find out area under such a curve. It is just integral of f of x, right? F means force will have some value at every x. It is integral of that f of x dx from initial position, starting position x equal to a to final position x equal to b, right? So work done is just area under the force versus displacement or force versus position curve. Okay, so this is a very simple concept. Yes, no, this is clear. Right. Okay, after that, now suppose the force is three-dimensional. So here we considered one-dimensional force only. Suppose force is three-dimensional. Okay, force is in 3D. So we can resolve it like this: fx into I cap plus fy into j cap plus fz into k cap. This is the force. And displacement. So small displacement dr bar can be resolved into dx into I cap plus dy times j cap plus dz times k cap. So this is component of displacement in x direction, this is component in y direction, this is component in z direction. Then we just learned yesterday that work done is the dot product of force and displacement. So work done is equal to f bar dot dr bar, right? We learned that work done is f bar dot dr bar. So that is equal to fx dx plus fy dy, right? Multiplying x component with x component, multiplying y with y, multiplying z component with z component. So fx dx plus fy dy plus fz dz. And then for total displacement from initial position to the final position, okay, initial position to final position, how much would be the work done? Work done is just integral of this dw. Dw is the small work done for displacement dr bar. So for the total displacement, we have work done is equal to integral of this dw, which is integral of this f bar dot dr bar. And what is f bar dot dr bar? It is fx dx, fy dy and fz dz. I mean fx dx plus fy dy plus fz dz. Now what will be integral of this? So see, starting point will have initial x, y and z position. Okay, so you can call it x1, y1, z1, and end point will have x, y and z position. Okay, x, y and z coordinate, x2, y2, z2. So then this fx dx has to be integrated from x1 to x2. Okay, so this is great simplification, right? It does not depend on y and z, so you have to integrate it from x1 to x2. F by dy has to be integrated from y1 to y2, and fz dz has to be integrated from z1 to z2, right? So this thing is clear, everyone. So this is the total work done from the starting position to end position. Okay, good. So then now let's see some simple problems based upon this thing. So the force on a particle moving in a straight line varies with distance d as shown in figure. Okay, the work done on particle during this displacement of 12 meters is, this is very simple. Force at the starting as it is 0, then force at 3 meters it's equal to 2 newtons, and then it falls off like this. Okay, it goes like this, it is constant till 7 meters and then it falls off. So we just learned what is the work done. It is area under this curve, right? Area under force versus x curve or force versus d curve. So how much is that area? This 2 times 4, okay, option D, 2 times 4, that's 8, 8 plus this is 5, yeah, 8 plus 5, 13, right? So 13 joules, okay, that is the area under this curve, total area of this rectangle plus area of the triangle. Okay, so this is very simple, right? This is from 2011 AIPMT. Let's see next one. A force acting on an object varies with distance x as shown here. The forces in Newton and x in meter. The work done by the force in moving the object from x equal to 0 to x equal to 6 meter is. So how much is the work done? It is area under this curve. So this is 3 times 3, so it's 9, okay, and this is half of base into height. So this much distance is 3, again this is half of 3 times 3 means 4.5, right? 9 plus 4.5, how much? 13.5. So work done is equal to area under fx curve or fd curve, right? So that is equal to what? Here it's 13.5 joules. So this is very, very simple. Yes, you need to take sign, you need to consider sign. So here both the areas are above x-axis, so they are positive. If it is below x-axis, it would be negative, right? It is always the case. Okay, so if it is an integration, it means that it is the signed area everywhere. Okay, this thing is clear, everyone? Okay, for an example, let's take an example. So suppose you have a curve like this. This is a sine curve. Like this. Okay, then how much would be the work done? How much would be the work done from starting position? Let's say this is the starting position. Okay, so t equal to 0, right? The particle is at x equal to 0 and this is some position at t equals to capital T. Okay, so this is, let's say, x equal to a or something like that. So how much is the work done in this case? It is signed area under this curve. Okay, so work done from x equal to 0, work done from x equal to 0 to x equal to a is signed area or area with sign under the curve, under fx curve, and this is very clear that this one would be positive and this is below the x-axis, so this area is negative, and that's why this is equal to 0, right? So this is positive, this is positive, this is negative, and therefore total area is 0. So work done is equal to 0. This thing is clear, everyone? Then let's see next sum. A force F equal to 20 plus 10y acts on a particle in y direction, where F is in Newton and y in meter. The work done by this force to move the particle from y equal to 0 to y equal to 1 meter is. So again, this is very simple problem. This is from 2019, that means it is designed by NTA. Okay, but it's very simple, right? So what is the work done here? So you can see that force is directed in y direction and displacement is also in y direction. So we don't need to consider anything else, right? Fx dx or fz dz. Just take f times dy because force is in y direction. Okay, from some initial position y1 to final position y2. Okay, so just put the values. So it is 20 plus 10y dy, integration of that from initial position 0 to final position 1. So that is integration of 20 dy. So 20 you can move outside, integration of dy from 0 to 1 plus integration of, again 10 you can move outside, y dy from 0 to 1, and then it's very simple. So what's the integral? Integral of dy is y and lower limit is 0, that means we need to just substitute upper limit. So this is 20, y goes from 0 to 1 plus 10, then integration of y dy is y square by 2, right? Then put the limits, so what do we get? So 20 multiplied by, put upper limit, that is 1 minus lower limit is 0, plus 10 multiplied by, let's take 2 outside, so then put 1. Okay, so it is 1 square, y equal to 1, 1 square minus y equal to 0, 0 square, so 1 square minus 0 square. So that is equal to 20 plus 10 divided by 2 is 5, 5 times 1 is 1, 5 times 1 is 5. So the answer is 25. Okay, it's there. It is option D, right? So again, this is very simple. Okay, good. Let us see next one. So a position dependent force. A position dependent force is this one. F is equal to 7 minus 2x plus 3x square. F is equal to 7 minus 2x plus 3x square Newton, acts on a small body of mass 2 kg and displaces it from x equal to 0 to x equal to 5. The work done in joule is. So again, this is similar to that of last one, but this is along x-axis, that's it. Okay, so earlier one was along y-axis, this one is along x-axis. So that doesn't mean there can't be any general problem, right? So they can give force like this one also, some fx times I cap plus fy times j cap plus fz times k cap. So they can give 3-dimensional force. Okay, so it's better to know the general case also. All right, so what is the work done? Just integration of f dot dx from x1 to x2. So again, this is very simple. So x1 is 0, x2 is 5. Okay, 0 to 5. So option A. Let's check. 7 minus 2x plus 3x square. Let's integrate that. So 7 you can move outside, integration of dx from 0 to 5, minus 2 you can move outside, integration of x dx from 0 to 5, plus 3 you can move outside, integration of x square dx from 0 to 5. So it is just integration of dx is x from 0 to 5, okay, 7 minus 2 times integration, so it's x square by 2 from 0 to 5 plus 3 times of x cube by 3 from 0 to 5. So this 3, 3, 2, 2 gets cancelled out, and then you put x equal to 5 because lower limit doesn't matter, it's 0, okay. So 7 times 5 minus 7 times 5 minus 2 times 5 square, okay, and then you have plus, oh, 2 cancelled out, no, sorry, 2 got cancelled out, this 2 is cancelled out. So x cube is what? 5 cube, that is 35 minus 25 plus 125, so that is 135, right, 135 joules. This is the answer, okay. So it is option A, right. So this is very, very, very simple, okay. So this is these are some of the simplest problems from this chapter, right, and most of the chapter is simple, okay. Let's see the next part, that is the kinetic energy, and we know what is kinetic energy, right. So it is energy associated by the energy possessed by a body due to its motion, okay. Kinetic energy is energy possessed by a body on account of its motion, and we know that it's equal to half of mv square. This is the kinetic energy, okay. So now suppose instead of this formula, okay, I want to write down formula in terms of momentum. So if P is equal to momentum is equal to mv, we know momentum is equal to mass times velocity, then what do we do here? So you can multiply and divide by mass, so you get m square v square, okay, numerator, and in denominator you will have m. So you multiplied with m and you divided with m. So what happens? This m square v square becomes what? P square. So this is momentum square. So kinetic energy has this another formula, p square by 2m, okay. So momentum square by 2m. So sometimes they say that two bodies have equal momentum, okay, and their masses are this and that, and then what is their kinetic energies, okay. So there can be questions like this, so we need to remember this one as well as this one, okay, both formulae. That's very, very simple, right. Okay, so kinetic energy has two formulae, half mv square, and second one in terms of momentum is p square by 2m. Same formula, but in terms of momentum p square by 2m, okay. All right, so next let's talk about the work energy theorem. Now what is this thing? So suppose let's talk about the work energy theorem in context of a constant force and a variable force, okay. So from third kinematic equation of motion, we can say that v square is equal to u square plus 2as, okay. V square is equal to u square plus 2 times a into s. We know a is acceleration, and for a constant force a would be constant, then only we are able to write down this formula, okay. V square is equal to u square plus 2as, okay. So then you can say that v square minus u square, just take u square on that side, okay, or we also remember this formula like this, v square minus u square is equal to 2as, and then just multiply by 2, multiply by mass and divide by 2, okay. Multiply with mass, all terms, m and divide by 2. So then what do you get? So if you do that, see, divided by 2, okay, so this 2 gets cancelled out, so you will have half v square minus half u square. If you multiply by m to each and every term, then you have half of mv square minus half of mu square on right hand side, and on left hand side you have multiplied by mass. So what is mass times acceleration? It is the force, okay. So what do you get basically is force times displacement is equal to half mv square minus half of mu square. So then you call this thing as final kinetic energy and this thing as initial kinetic energy, and this is the work energy theorem. Work done on an object by a constant force is equal to what? W, it's equal to change in kinetic energy. So work done results in change in kinetic energy. This is clear, everyone? Okay, so this is work energy theorem. All right. So then this is not just applicable for a constant force, it is also applicable to a variable force. Let's see how. So suppose for a variable force F, it causes small displacement dx, okay, in some time dt. Then work done in the small time interval dt would be equal to what? dw is F dot dx. Okay, for simplicity we are taking one dimensional case only. So the total work done from position x1 to x2 would be just integration of this thing, right? Work done is integration of F dot dx from x1 to x2. Okay, then you can say that force is equal to mass times acceleration, and we are not considering that acceleration is a constant. Okay, we are just writing that it's acceleration. Okay, and then acceleration we are writing as dv by dt. So here we didn't consider that it's a constant, right? It comes from whatever is formula for velocity in terms of time. So let's say 3t square plus 2t etc. Take derivative of that, okay, and it's equal to, for an example, 6t plus 2, right? So it is not a constant, okay, it depends on v. So you are taking derivative of that. So then what do you get? Now you can move this dt on this side. So you have m into dv multiplied by dx by dt. And what is dx by dt? So dx by dt is also v, okay, it is v. So it's integral from x1 to x2 of m v dv, right? But then this is x1 x2 and this is what? Velocity. Okay, so you can say initial velocity was u at x1, final velocity at x2 is v. So you change the variables from x to v, okay, because we want to relate work and kinetic energy. So then you integrate mv dv from u to v, from initial to final velocity, and by doing that, what do you get? M you can move outside, mass is a constant. Okay, integration of v dv gives v square by 2. Okay, that gives v square by 2. Put upper limit and put lower limit. So put upper limit. So putting upper limit, this thing is v square by 2 minus put lower limit. So it is u square by 2. Okay, and then multiplying with this m, again you get the same thing, half mv square minus half of mu square. So work done is equal to half of mv square minus half of mu square, means it is equal to final kinetic energy minus the initial kinetic energy. Okay, so this is again the work energy theorem. It's applicable for a constant force, it is applicable for a variable force too. Is this thing clear to everyone? Right, good. So now based upon this thing, let us see some problems. So a particle of mass m1 is moving with velocity v1 and another particle of mass m2 is moving with velocity v2. Both of them have same momentum, but their different kinetic energies are E1 and E2 respectively. Okay, if m1 is greater than m2, then tell me which one is correct. What is given? Same momentum. So which formula should you use for kinetic energy? E1 is equal to p square by 2m1, right, and E2 is p square by 2m2. Okay, because kinetic energies, they said kinetic energies are E1 and E2. Okay, we need to compare kinetic energies, right? Momentum is same, that's why we used this formula. Okay, formula in terms of momentum. Then you can just divide them, or you can just say that if momentum is constant, kinetic energy is inversely proportional to mass, right? So either you divide these two, or you can say that E is equal to p square by 2m. Okay, so kinetic energy is inversely proportional to mass if momentum is constant, right? So therefore E1 by E2 is equal to m1 by m2, m2 by m1, sorry, m2 by m1. It's inversely proportional. Okay, you divide this one by this one, you get this thing. So which one is greater? m1 is greater. m1 is greater than m2 means E2 is greater than E1, right? E2 is greater than E1. So this is correct. Okay, which option? Option A, E2 is greater than E1. Okay, good. So Vishalini found it out. Okay, so this is very simple, right? Okay, good. Let's see next one. If kinetic energy of a body is increased by 300%, then percentage change in momentum will be. Tell me very quickly. Kinetic energy is increased by 300%, then percentage change in momentum will be. Yeah, what will be the percentage change? Option B, you said 150%. Okay. Anyone else? Okay, let's see. So kinetic energy is given by P square by 2m, right? So kinetic energy, let's suppose initial kinetic energy was E1 is P1 square by 2m, okay, and it is increased by 300%. That means final kinetic energy is E2 is equal to E1 plus 300% of E1, means 3 times of E1, right? So E2 is 4 times of E1. Okay, E2 is equal to 4 times of E1. Then now what would be the percentage change in momentum? So you can say that E2 by E1, or let's take E1 by, no, let's take E2 by E1. So mass remains constant. So this is equal to P2 square by P1 square, right? So E2 by E1 is 4. So that is P2 by P1 square. And therefore what is P2 by P1? P2 divided by P1 is equal to 2. Okay. So P2 is 200% of P1. Okay. If you multiply this thing by 100, you get 200. So this is 200%. That means how much is the increment? Increment is 100%. Right? Is this thing clear? Okay. So if kinetic energy increases by 300%, increment in momentum is 100%. Alright, good. So don't jump to the conclusion that fast. Right? Question is simple, no doubt, but it's not 150. Alright. Let's see next one. Two bodies with kinetic energies in the ratio 4:1 are moving with equal linear momentum. The ratio of their masses is. This one is very simple. Yeah, two bodies with kinetic energy in the ratio 4:1. So E1 is to E2 is equal to. So we know that, oh, there is some shortcut here which gets activated. Alright, so E1, we know that E is proportional to what? E is inversely proportional to mass, or E is equal to P square by 2m. If P is constant, then E is inversely proportional to mass. So therefore you can say E1 by E2 is equal to m2 by m1 and this thing is what? 4 is to 1. So m2 is to m1 is 4 is to 1. That means what is m1 is to m2? It's 1 is to 4. Right, this is equal to 4 is to 1, that's m2 is to m1, and that means m1 is to m2 is 1 is to 4. Okay, so that's very simple. So see, 4 is to 1 is also there. Okay, all right, so that was very simple. 1 is to 4 is the answer, right? Let's see next one. A particle is projected making an angle of 45 degrees with horizontal, having kinetic energy K, not key. The kinetic energy at highest point will be, tell me. A particle is projected making an angle of 45 degrees with horizontal, having kinetic energy K. The kinetic energy at highest point will be. Anyone? Yami says option B. Yeah, that's correct. Correct. Okay, so you should not forget the previous points, right? Previous topics. All right, so what happens here for the case of projectile? So this one is projected at 45 degrees. So its initial velocity is u, suppose. Then you have two components, right? Ux and uy. So ux is just equal to u cos of theta, but theta is 45 degrees. So that's u cos of 45, and ui is u sin 45. Okay, so this is ui is u sin 45, right? So then at highest point we know that it has only one component of velocity, that is the horizontal component of velocity. Okay, so that is ux, and therefore kinetic energy at beginning is equal to half of m into u square. Okay, ke is half m into u square. Let's say this is E1, and kinetic energy here it's E2. So what is E2? It is just half of m into ux square. And how much is ux? U cos 45. That means cos 45 is 1 by root 2. So it is u by root 2. So take square of that. So it is u by root 2 square. Okay, so that is half of m into u square divided by 2. That means it is E1 by 2. Okay, so they are calling it as k. So it is k by 2. Very, very simple. Right? Yes, no? Okay, so I guess actually this problem was given in the homework sheet of projectile motion, right? It was there, no? In the class problems or in homework sheet, somewhere it was there, if you remember. I'm definitely sure. Okay, I'm very sure that it was there. All right, let's see next one. A ball of mass 2 kg and another of mass 4 kg are dropped together from a 60 feet tall building. Okay, after a fall of 30 feet each towards earth, their respective kinetic energies will be in the ratio of. A ball of mass 2 kg and another of 4 kg are dropped together. Which one will move faster? Anyone? Okay, option C is the answer. Let's check. Same speed. Yeah, that's correct. Okay, so both will move with the same speed, right? Acceleration doesn't depend on the mass. Okay, so a ball of mass 2 kg and another of mass 4 kg are dropped together. So they are dropped from 60 feet. After a fall of 30 feet each towards earth, their respective kinetic energies will be in the ratio of. So then kinetic energies are in the ratios. E1 by E2 is equal to half of m1 v1 square divided by half of m2 v2 square, and since they will have same speed if they fall through same height. So v1 and v2 gets cancelled, and that's why it is just m1 is to m2, and that is 2 by 4, right? So this is just 2 by 4, that means 1 by 2. So option C is the answer, correct. Okay, so very simple question, right? Right, this one is very simple. Okay, let's see next one. A body of mass 3 kg is under a constant force, which cause a displacement s in meters in it, given by the relation s is equal to 1 by 3 t square, where t is in seconds. So work done by the force in 2 seconds is, tell me. Now I have told earlier that if s is proportional to t square, if there is t square in the formula, then what you should do? What should you do? You should compare that with s is equal to ut plus half at square, right? Okay, so from that you get u equals to 0 and half a is equal to what? 1 by 3, and therefore a is equal to 2 by 3, right? So you got acceleration, and this is constant acceleration. So work done by the force in 2 seconds is, what will be the work done? Okay, so from this one you can find out v. What will be v? V is just u plus at. Okay, and we want specifically at t equal to 2 seconds. All right, let's put acceleration. So this u is 0, acceleration is 2 by 3 times t. Okay, so this is the formula for v. It's 2 by 3 t. So how much will be the work done? Tell me. Work done is just final kinetic energy minus initial kinetic energy. Okay, kf minus ki, final kinetic energy minus initial kinetic energy, that is half of m into v square minus half m u square. But it's given means we just found that u is equal to 0, right? U is equal to 0. U is 0, and therefore it is just half of m into v square. And what's that? It is just half m multiplied by 2 by 3 t square, right? 2 by 3 t square of that, and that is half of, what is m? It is 3. Then 2 by 3 square is 4 by 9 t square. How much is t? 2 seconds, right? So 2 square. Okay, so this 2 gets cancelled out with this one square. Okay, so 4 times 2 is 8, then 3 by 9 is 1 by 3. 8 by 3 is the answer, right? So 8 by 3 joules, this is the answer, option D. Okay, right, this is clear everyone? Selva Kumar?
Clear, sir.
Okay, how did we find the work? By using the work energy theorem, right? We use the work energy theorem. Okay, all right, so whenever you have s in terms of t square, whether there is some term of t and one term of t square, but there is no t cube and higher terms of t, then just compare that with s is equal to ut plus half at square. Okay, all right, let's see next one. A force acts on a 3 gram particle in such a way that the position of particle as a function of time is given by this thing, where x is in meters and t in seconds. The work done during the first 4 seconds is. So once again, what should we do? Work done is change in kinetic energy. So just find out initial and final velocity. So for that we know v is equal to dx by dt. right? So that is d by dt of 3t minus 4t square plus t cube. Take its derivative. So derivative of this one is 3, right? It is 3 times dt by dt minus derivative of 4 times derivative of t square. Okay, 4 times derivative of t square is 2t plus derivative of t cube is 3t square. So that is equal to 3 minus 8t plus 3t square, right? And then what is u, what is v? So u is equal to, just put t equal to 0. Okay, at t equal to 0, u is equal to what? Just 3 meters per second. Okay, and what is v? V is at 4 seconds, right? At 4 seconds, at t equal to 4, v becomes what? Put the values. 3 minus 8 times 4 minus 3 times 4 square. So that is, v is equal to 3 minus 32. Okay, so third term is positive, right? So 3 times 4 square, so 3 times of 16, how much? 48. Okay, so 48 minus 32 is 16, 16 plus 3 is 19 meters per second, right? Right. Okay, then just find out the work done. So work done is equal to final kinetic energy minus initial kinetic energy, that is half of m multiplied by v square minus u square. Okay, that is half of m is 3 grams, so 3 into 10 raised to minus 3 minus multiplied by 19 square minus, what's that, 3 square. Okay, so just carry out the calculation. Right, now suppose I don't know what is 19 square, and I really don't know. So what I will do is, it's 19 plus 3 multiplied by 19 minus 3, right? That is 19 plus 3 is 22. Okay, 22 multiplied by 16. Oh, so half of 3 multiplied by 10 raised to minus 3 multiplied by 22 multiplied by 16. Okay, then you can cancel out something from here. 22 divided by 2 is 11, so it is 3 times of 16, that's 48. 48 multiplied by 11 multiplied by 10 raised to minus 3. Okay, so that is 480 plus 48. Okay, so 528 into 10 raised to minus 3, that many joules. It's not correct. Yeah, 530, near about 530 you can say. So it's option D, right? So 528 into 10 raised to minus 3 joules is nearly 528. It is 528 millijoules. Okay, and nearly you can say 530 joules. 530 millijoules. So this thing is clear? Yes, no? Okay, problem is simple, right? Okay, very good. So similar problem, this is also similar problem, but here we need to take derivative, because here t, the relation between x and t, so it doesn't end at t square term, there is t cube term also, right? All right, then let's see next one. The kinetic energy acquired by a mass m in traveling distance d starting from rest under the action of a constant force is directly proportional to. Force is constant, so what is the work done? Work done is equal to force times displacement, right, because it's a constant force. So for a constant force we know that work done is just force times displacement for a constant force. And therefore now how does it depend on the mass? Does it depend on mass? Okay, they say that kinetic energy acquired by mass m in travelling distance d starting from rest. So we know from work energy theorem that work done is equal to final kinetic energy minus initial kinetic energy, and starting from rest means initial kinetic energy is equal to 0, ki is equal to 0. Okay, so work done is equal to kf. That means kf is equal to what? F times d. Okay, so kf is just equal to force times displacement. How does it depend on mass? Anyone? Does it depend on mass? Does the mass come anywhere? Force is there which is constant, displacement is there. No, it doesn't depend, right? It does not depend. That's the answer. Okay, is this thing clear? The answer is this thing, m raised to 0. Right, any confusion? Anybody? Nikita, this is clear? Okay, good. All right, let's see next one. A particle of mass m at rest is acted upon by a force p for a time t. Its kinetic energy after an interval t is. Okay, tell me. Now they are calling force by the name p. Okay, so it is not momentum. So this is force, right? All right, no problem. So p is force and we want kinetic energy after an interval t. Okay, so what is force? It is mass times acceleration. So I can say m times v minus u by t. Okay, and it starts from rest. That means u is equal to 0. Put u equals to 0, right? Then you get m times v is equal to, see here, m times v is equal to pt, p times t, force times t, and this thing is momentum, right? This thing is momentum, and therefore what I can do is, let's call momentum by small p or p dash. Let's say p dash is momentum, so it's equal to m times v, and therefore what is kinetic energy? So ke is equal to half of mv square, or we can say p dash square by p dash square by m, right? So that is half of p dash square. What is p dash? So it is pt square by m. So that is equal to p square, is capital P square t square by 2m. That's the kinetic energy, right? So it is p square t square by 2m. So it's option B. So this thing is clear. Okay, again this is also not difficult, right? Okay, let's see next one. Next one is next topic. So that is potential energy. Now what is potential energy? Where does it come from, etc, etc? Let's discuss these things. So it is the energy possessed by a body due to its position. This is the definition. which we have been studying from lower standards, right? 8th, 9th, etc. So let's take an example of gravitational force. Suppose you take this ball and you want to move it from here to here. So you know that gravitational force is acting downwards. So how much work do you need to do on that ball? So if you want to move it from this height h1 to this height h2, so height difference is h2 minus h1. Okay, so work done is equal to mg. Mg is the force that is acting downwards, so you need to exert force equal to mg upwards, right? And then work done will be equal to mg multiplied by the difference in height h2 minus h1, right? So now this work done does not depend on the path followed. Okay, work done will be always equal to mg multiplied by h2 minus h1. So when you move it from here to here, work done is same. Okay, suppose you move it from here to here, there is no work done, right? No work done against the gravitational force, because the force and displacement, they are perpendicular to each other. So gravitational force does not care. Gravitational force doesn't care how you move it at the same level. Okay, if you are moving it or if you are not moving it, so gravitational force doesn't care about that. This thing is clear? Yes, no? There will be no work done if you move it at the same height. Okay, if you don't change the height, there is no work done against the gravitational force. Then you move it from here to here, again the work done would be equal to what? It is against the gravitational force, so mg multiplied by h2 minus h1. And then you move it from here to here, no work done. So you move it along this path or this path, it's same, the work done will be equal, right? Okay, then similarly you can say that this path, which looks something like this, etc., it can be resolved into what? You take small displacement. Okay, let's say I take this small displacement, I can resolve it along two components. One is along x-axis, that is horizontal component, and another is along y-axis, okay, that is vertical component. So gravitational force just opposes this vertical displacement, right? So we need to do work for this vertical displacement only, and if you add up the small vertical displacements, okay, what will you get? You will finally get only the height difference, right? That means work done in that case, in any case, is also same, right? This thing is clear? Yes, no? All right. So work done against the gravitational force in along any path is equal. So this kind of a force is known as a conservative force. So what is a conservative force? Work done against such a force, or work done by such a force to move an object from some initial position to final position, okay, between same 2 points, is always equal. It does not depend on the path followed. Okay, so work done does not depend on the path followed, means the force is conservative force. Work done by force also and work done against the force also does not depend on the path followed. Okay, so then what we can do is, for such a force, only for such a force which is conservative, that means work done does not depend on the path followed, for such a force we can define a function of position which is called as potential energy. Okay, we can say that it has some fixed potential energy. It means that object has fixed potential energy at starting point and it has some fixed potential energy at the end position. When you do some work against the conservative force, it increases that energy. Okay, we can express work done against the conservative force as W equals to sum U2. U2 is what? It is some function of position at this final position minus U1. Okay, work done is U2 minus U1. We call U as a potential energy. So it is some function of position, okay, and we calculate it at final position minus initial position. So now what will that be? For this gravitational force, U is definitely equal to mgh, because what is the work done? It is mgh2 minus mgh1. So only height matters, no? So that's why U2 is mgh2, okay, U1 is mgh1, and we call this mgh as what? The gravitational potential energy, right? Gravitational potential energy. This thing is clear? Yes, no? Right? U2 is the final potential energy, U1 is the initial potential energy. Okay. So now suppose there is a non-conservative force. For example, suppose I have this block and I want to move it from point A to B. Okay. I want to slide it from point A to B. So I exert some force, and here I need to do some work against what? Against the frictional force, and I move it from A to B. Then there would be some work done. Then if I move it back, there would be same amount of work done, and then again if I move it from A to B, what will happen? The work done will be 3 times, right? So it depends definitely on the path followed, right? Work done depends on the path followed, and that's why this kind of a force is known as a non-conservative force. So the force for which work done depends on the path followed, work done by the force against the force depends on the path followed, it is called as a non-conservative force, right? Friction is one example of non-conservative force. Okay, so you cannot define a potential energy for this kind of a force. This thing is clear? Right? Very good. Then let's see the relation between a conservative force and potential energy. So now we know that work done against a conservative force by external force, the work done would be equal to what? Final potential energy minus initial potential energy. So let's suppose this is just small change in the position. So we write this change in potential energy as du, right? What is du? It is final potential energy minus initial potential energy. So for a one-dimensional case, let's say for x-axis, I can say that external force multiplied by displacement is equal to du. Okay, this thing is clear. External force times dx is du. Okay, work done against the conservative force is done by what? It is done by external force. So it is just force into displacement. And we can say for a small displacement, okay, very small displacement, force is constant, right? So I can just say that it is force times displacement, but it is external force times displacement. This is equal to du, right? So then take that dx on other side. So how much of external force do you need to exert? Do you need to apply? That is equal to du by dx. And then what's the relation between the external force that you apply and the conservative force? That means in case of gravitational force, suppose force mg acts downwards, how much force do you need to exert to counter it? It's equal to mg, but gravitational force is negative, this one is positive, right? So there is sign difference between the two forces, external force and the conservative force. So external force that you need to exert is just negative of the conservative force, and that's why what do you get? Take that negative sign on the other side. So the conservative force is equal to minus of du by dx. The conservative force is equal to what? Minus of du by dx. Is this thing clear? Yes, no? Okay, so we say that conservative force is equal to negative of gradient. So this thing is called as gradient. Okay, change in something, some quantity with respect to distance. Okay, so conservative force is equal to negative of gradient of potential energy with respect to position, right? So this is the formula. Now see, so suppose I want to take an example. Just to take an example, let's take an example of gravitational force. So gravitational force it depends on y-axis, right? It changes, I mean the gravitational force acts on y-axis, okay, right? So therefore, now if you want to write down formula for the potential energy for that, so U will be equal to what? I want to write a variable, so I can write mgh also. In that case, h will be a variable, or I can say it is mgy, okay, mgy, y is just h, okay. So what is the gravitational force? So this is for the case of gravitational force, okay. For gravitational force, right? So U is equal to, you have mg y is suppose height, and therefore what is the gravitational force here? Gravitational force is the conservative force, so it's equal to minus of du by dy, right? And that is equal to minus of dy of mgy, and out of that m and g are constants, so you can move them outside, right? You can move them outside, and therefore what do you get? That's equal to minus of mg into dy by dy, so that's equal to minus mg, and we know that gravitational force is minus mg, right? So negative sign tells that it acts along negative y-axis. So this thing is clear? Yes, no? Okay, everyone? Good. So this is how we can find out the relation between, not relation between, given the potential energy, we can find out the force. Okay, all right. But in general, we know that force is a vector quantity, so it will have x, y and z components, 3 components. So F bar can be written as Fx into I cap plus Fy times j cap plus Fz times k cap. So there are 3 components of force: x component, y component and z component, right? So that means your potential energy must have 3 coordinates, okay, it must be a function of 3 coordinates, right? It must depend on x, it must depend on y and z, okay. So therefore, how will you find out the x component of force? Just take derivative of potential energy with respect to x, okay. So you write minus of, I will just say du by dx, but this is not du by dx, this is called as dou u by dou x, okay. So now this is not your usual derivative, this is called as a partial derivative, okay. So this is read in several ways, so dou u by dou x, or you say del u by del x is also fine, or you say that partial derivative of u with respect to x, or partial u partial x. So several names, right? I mean different people call it different ways. Okay, so what is this thing? Just understand what is this thing. While taking derivative with respect to x, this is partial derivative of u with respect to x. While taking derivative with respect to x, you will treat y and z as constants, so then you say that you are taking partial derivative, okay. When you take derivative with respect to x, you treat y and z as constant, then that is a partial derivative. This thing is clear? What does this sign mean? This sign means that in place of d you are writing dou, okay. What does that mean? It means that while taking derivative of u, what are you doing? What you are doing is, when you take derivative with respect to x, you will treat y and z as constants. When you take derivative with respect to y, you will treat x and z as constant, and when you take derivative with respect to z, you will treat x and y as constant, okay. So then that kind of derivative is known as partial derivative. So how do you get fx? Minus of partial derivative of u with respect to x, fy is minus of partial derivative of u with respect to y, and fz is minus of partial derivative of u with respect to z. Just put that in this formula, so you get f bar is equal to minus of dou u by dou x times I cap plus dou u by dou y times j cap plus dou u by dou z times k cap, right? This is curly d, that is called as dou, okay? Or you can just say partial, okay? Partial u, partial x, okay? Or del is also fine, but this sign is called as del, okay? So let me explain this. So this thing is clear till this point. Okay, now this thing is a little extra, but it's good to know. I mean, just good to know, okay? There is no use case of this thing in NEET, okay, or JE also. So f bar is equal to minus of, this thing can be written in short form like this with this symbol, okay? Minus of, this is called as del operator, this symbol is called as del operator, or you can call it gradient operator also, right? It is called as gradient operator or del operator, del operator. So this symbol is called as del. What does del mean? Del means I cap into dou u by dou x, that is partial u, sorry, I said u, I cap multiplied by dou x, okay, plus j cap multiplied by dou y, plus k cap multiplied by dou z, okay? So it will act on something, suppose it acts on u, then these operators, they will act on u, okay? So then it means that you will multiply this thing with u. It's not multiplication, you're operating u with this operator, okay? So right, you're operating u with this thing, then you get this thing, okay? Is this thing clear? So this is just short form of this thing, okay? This is just short form. We have written this thing in using a symbol, we can say, nothing else, but you need to remember this formula. This formula is clear? Yes, no? Yes, no? Tell me. All right. So what we'll do is, we'll just quickly take an example of this thing, okay, so that it becomes very clear. So let's suppose u is equal to x, y, z, that's it, okay? So I want to find out the conservative force, find the conservative force. So Fc is equal to, you have I cap, negative sign I will take outside, I cap multiplied by partial derivative of u with respect to x plus j cap multiplied by partial derivative of u with respect to y plus k cap times partial derivative of u with respect to z, right? So that is minus of I cap multiplied by what is u, so it is x, y, z, okay, plus j times dou by dou y of x, y, z plus k cap times dou by dou z of x, y, z. Now just take the partial derivative. So take y and z outside, or any function of y and z outside, okay, because they are constants, right, when you take derivative with respect to x. So move them outside, so you have yz, and then what is derivative of x with respect to x? It is 1, okay? So this thing gives minus of yz times I cap plus this thing gives you, take x and z outside, then dou y by dou y is 1, okay, it's just like ordinary derivative, then so it is plus xz times j cap plus, from the last term you will have xy times k cap. So this will be the conservative force, right? So this thing is clear? Clear, not clear? Okay, good. Then there can be a question like this, u is equal to this thing, find the force at some position, okay, 1, 2, 3, then what will you do? Just find out this thing and put x equal to 1, y equal to 2 and z equal to 3, right? Okay. So in this case, for an example, in this case it will be equal to what? Minus of, at position at some point 1, 2, 3, this thing will be fc bar is equal to minus of y times z. So it is 2 times 3 into y cap plus x times z is 1 times 3 into j cap plus x times y is 1 times 2 into k cap. So 6 I cap minus 6 I cap plus 3 j cap plus 2 k cap. Okay, so this is how we will solve this kind of a problem, right? So this was asked very few times and very earlier, but still we should know this, okay, because this thing is used not only here but it is used in electrostatics also, right? Because electric field, we'll see that electric field is found by using gradient of the potential, electric potential. Okay, all right. So let's talk about the equilibrium of a particle under a conservative force. Now what does an equilibrium mean? Equilibrium means the net force is equal to what? 0, right? Net force is equal to 0. So there is only conservative force acting on the particle, only conservative force acting on the particle, then F is equal to 0 means what? Du by dx should be equal to what? It should be equal to 0, right? Force is 0 means gradient of potential energy, not potential, gradient of potential energy with respect to position is equal to 0, right? Actually gradient is always taken with respect to position only. Okay, so gradient means you are taking derivative with respect to position. So gradient is equal to 0, right? So that means del u is equal to 0, all three derivatives of u, that means with respect to x, with respect to y, with respect to z, partial derivatives are equal to 0. Okay, so at equilibrium. Now there are two types of equilibriums. So one is stable equilibrium, the other one is unstable equilibrium. Okay, so what is a stable equilibrium? So a stable equilibrium is when the potential energy is minimum. Unstable equilibrium will be when the potential energy is maximum. Okay, so see here, you have force acting on this particle. Okay, sorry, at this position the potential energy is 0. Okay, and then suppose you move it like this, what will happen? If you move it over here, what will happen? There is gravitational force acting on this particle, right? So one component of gravitational force would be perpendicular to this plane and one component would be parallel to the plane. So component parallel to plane is mg sine theta. Okay, if this plane is inclined at an angle theta, then we can find it out. Okay, so mg sine theta will be directed towards this position, or it will be it will result in taking this particle or this object towards the mean position. Mean position means the equilibrium position. Okay, this thing is clear? Yes, no? And what will the other component of this gravitational force do? It will balance the normal reaction. It will balance the normal reaction, right? So when you move this object away from the equilibrium position, then what happens? There is a component of force. There is a force, net force acting on the object towards that equilibrium position, right? That force tries to take the particle towards the equilibrium position. So this is called as a stable equilibrium, because if you displace the object, what will force do? There will be if you displace the object applying some external force, you remove the external force, then the force acting on the object, the conservative force acting on the object, will be towards the mean position. Okay, and here If you displace it, then now again you can resolve, right? There will be mg gravitational force acting on it. You can resolve it perpendiculars to plane and along the plane. That along the plane component, what will it do? It will move it away from this equilibrium position. Okay, so it will never come back. Okay, so this thing is equal. Is this thing clear? Yes, no? Okay, so this thing is called a stable equilibrium, because even if you displace the body, it will come back to the same position. And this one is called as unstable equilibrium, because if you displace the object, then it will never come back to the same position. Okay, good. Then suppose this is u versus x curve. Now again we are taking one dimensional example, that u is suppose only function of x. Then at the position of minimum of potential energy and maximum of potential energy, du by dx will be equal to 0, right? That is, the object is in equilibrium, stable or unstable. Okay, so at minima also it is in equilibrium, at maxima also it is in equilibrium, because at minima the potential energy is minimum, that means its derivative is 0, that means force is equal to 0, right? We just saw that conservative force can be written as minus of du by dx. Okay, so at minima du by dx is 0, means conservative force is equal to 0. At maxima also the conservative force is 0, because du by dx will be 0. Okay, then if you take d2u by dx square at minima, then at minima it will be positive, we know this, and at maxima d2u by dx square is negative. Okay, so if d2u by dx square is positive, this is stable equilibrium. Okay, this is minima. At stable equilibrium, how is the potential energy? It is minimum. At unstable equilibrium, how is the potential energy? It is maximum. Okay, so we know, so we have studied this in mathematical methods, right? So at minima, second derivative is what? Second derivative is positive. First derivative is 0, second derivative is positive. And at maxima, the first derivative is 0 and second derivative is negative. So if second derivative is positive, means it is minimum, okay, or minima, that means it is stable equilibrium. Second derivative, second derivative of what? Second derivative of the potential energy, right? And if second derivative is negative, then it is a maxima, means it is unstable equilibrium. So this thing is clear, everyone? Right? Okay, good. Then let us discuss some problems based upon this. A gravitational field is present in region and a mass is shifted from A to B through different paths as shown. If W1, W2 and W3 represent the work done by gravitational force along respective paths, then, okay, it's W1 is equal to W2, it's equal to W3, right, correct. So it is option B. Okay, very good. Alright, let's see next one. A particle is released from height s from the surface of Earth. At a certain height, its kinetic energy is 3 times its potential energy. The height from the surface of Earth and the speed of particle at the instant are respectively. Tell me. It is released from height s. Okay, when it is here, all its energy is potential energy, is equal to potential energy. Then at some height, they say, let's say at this height, okay, what happens is kinetic energy is thrice. Okay, K is equal to 3 times of P. At a certain height, kinetic energy is 3 times of potential energy. Okay, so what is that height? So let me explain this. It's very simple actually. So if I divide this total height into 4 equal parts, so when I come to half of the height, what will be the potential energy? So at this height it is mgs, at this height it will be mgs by 2, right? So potential energy has become half, okay, and at this point it becomes 0, okay. So if I divide it in 4 equal parts, then what will happen? Potential energy, I can say that it increases by equal amount here, okay. So if this is, take some unit, in some unit it is 1, here it will be 2, here it will be 3, here it will be 4, right? So that means if it is 4 there, then from there if I want to decrease it to 1, because of what? If potential energy is 1, then remaining, okay, suppose it's 4 joule here and it becomes 1 joule at this point, then where does the remaining 3 joule go? It goes into the kinetic energy, okay. This thing is clear? Yes, no? Right. So therefore at this point, which is equal to what? This total distance is s, so this is s by 4. So there the potential energy is 1, then kinetic energy will be 3, right? So what is this height? It is equal to s by 4. So at h is equal to s by 4, okay. So you got the answer. And then you know, so to go from h1 equals to s to h2 equals to s by 4, okay, h1 equals to s to h2 equals to what? S by 4. How much is the question is height from the surface and the speed of particle. So how much is speed? We know v is equal to square root of 2g height difference, that is h1 minus h2. Just put that. So s minus s by 4, okay, so that is 3s by 4, right? So square root of 2 times of g times 3 times h by 4, sorry, s by 4, okay. So that 2 by 4 is 1 by 2, so 3gs divided by 2, that's the answer. 3gs divided by 2, it's option A, right? This is a simple question, it's from NEET 2021. Simple, no? Yes, everyone? Okay, good. All right, let's see next one. Potential energy of a system increases if work is done, okay. This is a very crucial point. Potential energy of a system increases if the work is done upon the system by a non-conservative force, by the system against a conservative force, by the system against a non-conservative force, upon the system by a conservative force. Tell me. It's option B, okay. Does everyone agree? Right, work done is against a conservative force, okay. Work done by the system against a conservative force, right? Is there any confusion in this? I am waiting, okay, because earlier students have asked me, they had some confusion with chemistry and thermodynamics. Yeah. So when work is done against a conservative force, then potential energy increases. Right? And now, see, just to give you an example, so if you get confused in by the system or upon the system, so suppose system is this, there is a ball, okay. Now you apply external force, or suppose it has internal kinetic energy and it moves upwards with kinetic energy half mv square, okay. It is moving upwards. So what happens if it is moving against the gravity? Then this is the system which is doing work against the conservative force, right? Will its potential energy increase? Potential energy, will it increase or decrease? It will increase, right? Okay, so that's the answer. If work is done against the conservative force, then the potential energy increases always. Okay, and now suppose there is some external agency, I mean there is some external force, you lift it, still what will happen? Still the potential energy will increase, right? If work is done against the conservative force. So this against the conservative force matters, okay, that is important. Okay, all right, so this is the answer. Okay, let's see next one. Now if work if W1, W2, W3 are the work done in moving a particle from A to B along three different paths 1, 2, 3 respectively as shown in the gravitational field of a point mass m, the relation between W1, W2 and W3 is. So this one you can clearly see that it is repeated in different exams. So it is just W1 equals to W2 equals to W3, right? It's option B, right? Let's see next one. The slope of potential energy versus position graph gives the magnitude of, tell me, potential energy versus the force. Option C, time rate of change of momentum, right? Correct. Okay, you have potential energy versus position. If you take slope of that, what do you get? If you take du by dx, then if you just take its magnitude, it's equal to conservative force, right? And what is force? So it is change in momentum divided by time, or you can say dp by dt. So du by dx magnitude is equal to what? Dp by dt, because force is equal to dp by dt. Time rate of change of momentum, that's correct, option 3. Okay, let us see next one. The potential energy of a particle in a force field is U is equal to A divided by R square minus B divided by R, where A and B are positive constants and R is the distance of particle from the center of field. For stable equilibrium, the distance of particle is, tell me. So for stable or unstable, du by dr must be equal to 0, right? It's equal to 0. So let's take du by dr. So d by dr is equal to A divided by du by dr of A divided by R square. So I will write this thing as A times R raised to minus 2, right? Minus B times R raised to minus 1. Now we can easily take derivatives. So what is derivative of this thing? So that is minus 2 multiplied by R raised to minus 3. Okay, if you remember formula is R raised to n, suppose is the function, and I want to take its derivative. So the derivative would be n R raised to n minus 1, right? So n is minus 2 here. Okay, so that it's minus 2 r raised to minus 2 minus 1 is minus 3, right, minus this minus 1, okay, times b to r raised to minus 1 means minus 2, and that's equal to 0. Okay, so again what we can do here is okay, so I can write this thing as minus 2 times a divided by r cube minus, so that minus minus will become plus b divided by r square, and that's equal to 0. It's option B. Let's check. So then you can take 1 by r common. Okay, you can take 1 by r common, 1 by r square you can take common, so it is then you're left with minus 2a upon r plus b is equal to 0. So you have two options here, either 1 by r square is equal to 0, right? If 1 by r is 0 means r is what? That means r square is 1 by 0, that means infinity. Okay, so r would be plus or minus infinity. So that is one option, right? And another option is, that option is not there. Another option is minus 2a by r plus b is equal to 0. That means it will be what? Minus 2a by r plus b is equal to 0 means b is equal to 2a by r, or r is equal to 2a by b, right? So that is the answer. It's option B. Okay, so almost every time we don't need to even check for the second derivative, right? All right, let's see this one. The potential energy between two atoms in the molecule is given by ux is equal to a by x raised to 12 minus b by x raised to 6, where a and b are positive constants and x is the distance between the atoms. The atom in the stable equilibrium when? So again, this is similar to the last one, and I just included this just to have some practice, right? Nothing else. Otherwise it's similar to last one. Just take derivative. So atom is in stable equilibrium when the du by dx will be equal to 0, right? So d by dx of this thing, a by x raised to 12 minus b by x raised to 6. So let's take derivative of that. So that will be minus 12a by x raised to 13. Okay, I am taking derivative directly now, and it will be minus 6b by x raised to 7. Okay, and then what you can do is you can move that x raised to 7 outside. You can take x raised to 7 common. So if you take x raised to 7 common in the denominator, you have minus 12a plus 6b, minus 12a divided by x raised to 6 plus 6b. So either x raised to 7, 1 by x raised to 7 is equal to 0, either 1 by x raised to 7 is equal to 0, right? Okay, let's check option A. Or second thing, 6b minus 12a by x raised to 6 is equal to 0. That means, if that is equal to 0 means we have 6b is equal to 12a by x raised to 6. Therefore x raised to 6 is equal to 12a by 6b. That means 6a by 2a by b. Okay, and then you take 6th root of that, so 2a by b raised to 1 by 6. Okay, so it is option A. That is the answer, right? So very, very simple. Yes, no, right? and if you want to check, you can take second derivative, and at minima second derivative should be positive. All right, let's see next one. A particle with total energy E is moving in a, okay, this one is, okay, let's see. A particle with total energy E is moving in a potential energy region U of X. Motion of the particle is restricted to the region when the total energy should be less than or equal to potential energy, right? Yes, no, total energy should be less than or equal to, sorry, I said opposite. Potential energy should be less than or equal to total energy, right? Let's take an example. For an example, let's take a ball, okay, it is released from here, just released from here. So at this point, its all energy will be potential energy. Then it goes down, okay, it will move till this height, again it will come down, right? So its potential energy gets converted to kinetic energy when it comes here, right? Total potential energy gets converted to kinetic energy. At this point, some part of its energy will be potential, some will be kinetic, okay? At the max, total energy is potential energy at this point as well as at this point, right? So potential energy can be at max equal to the total energy, or it is less than total energy. That's very simple. Yes, no? Okay, that's why this will be the answer. U of X should be less than or equal to E. Okay, good. See this question. Actually, we have solved a similar question. A particle in a certain conservative force field has a potential energy given by U equals to 20 xy divided by z. The force exerted on it is, let's solve this one quickly. So Fx is equal to, what will be Fx? Minus of dou u by dou x, right? That is equal to minus of, take derivative of that with respect to x, so that will be of 20 xy by z, derivative of 20 xy by z. Y and z are constants, you can move them out, so that's minus y by z, minus 20y by z, and then what remains is derivative of x with respect to x, so that is 1, right? So you got Fx. Similarly, you will find Fy. So Fy is equal to minus 20, similarly, okay, I am writing it directly, minus 20 x by z, right? Option 2, let's check. And Fz is equal to minus 20 xy, okay, x and y are constants, then take derivative of 1 by z, so that is minus 1 by z square, right? So that is plus 20 xy by z square, right? So that's correct, okay, 20 xy by z square. So you got Fz, and therefore what is the force? So force is equal to Fx into I cap plus Fy times j cap plus Fz times k cap, and put the values of Fx, Fy and Fz, then it comes out to be option 2, right? So this thing is clear. Yes, no? Everyone? Right. So this is how we will find the force given the potential energy, and also given the force we can find out the potential energy, right? Okay, given the force we can find out potential energy, and given the potential energy we can find out force. There is another method too. Another method means you can just integrate this and you can find out function for potential energy, right? Okay, so what I mean to say is, if f is equal to du by dx minus du by dx, just take du equals to f dx, actually it will be minus f dx, right? and then you integrate this. Okay, so what you will get is only difference in potential energy and not actual potential energy. Okay, you will only get difference in potential energy, not the actual potential energy if you integrate this. So that will be u at some position minus u at 0. Okay, and from that also, solving that, you can try to predict the graph, right? So that is another way. This thing is clear, everyone? All right, good. So now we'll stop here, and I will send you the homework problems. Okay, so please try to solve some problems. Okay, all right, welcome. So let's stop here. Okay.